Hello everyone and welcome to FEMM 4.2 course. In this video we are going to cover why FEMM 4.2. To answer this question, we need to have an idea about the finite element analysis. So let's start. What is finite element analysis? We need to select one of those. Is it a graphical tool to make pretty pictures? B, a perfect example for garbage in, garbage out. C, a powerful stress analysis tool. D, a mathematical tool for solving boundary value problems, or all the above? The answer is all the above. So in general, finite element analysis is to take a complex problem and break it into small pieces, a finite number of elements, simplify each piece, reassemble the pieces, solve the problem, for example, using matrix manipulation. So finite element analysis could be with different names: finite element method, FEM, boundary element method, finite volume method, finite difference method. In electrostatics or electromagnetics, finite element analysis solves boundary problems using differential equations such as Maxwell equations to find electric or magnetic potential. So in general, what are the steps of simulation using finite element analysis? Number one, problem identification. We need to identify a geometry. We're going to create a mesh. We're going to add the physical properties to our problem. Step number two, resolution. Choose numerical solution or iterative technique. Step number three, results analysis. Our problem is electromagnetic, so we can get flux density, field intensity, flux distribution, iron losses, inductance. And if our problem is electrostatic, we can have electric field, potential, capacitance, and more. We noticed in the previous slide that you mentioned creation of mesh. What do you mean by that one? So the finite element method works by dividing the problem domain into many small elements, something like that one. That one is called element. And the element consists of nodes, as you can see here. So each element is defined by different nodes. That one formed what we call it mesh, something like that one here. So the unknown values are calculated, and that one based on the problem is 2D or 3D. For example, if we have 2D problems, we can use triangular mesh, but for the 3D, we are going to use something like bricks, pyramids, and so on. So we noticed that you didn't explain that one in details. Why I need here in this course to give you a starting point to tackle the FEMM software. I'm not going to explain here. That one is not a course for finite element method. That one is a course as a starting point for FEMM software. So I prepare what I need. So the areas of applications for finite element analysis, they are plenty and uncountable. Something like mechanical engineering design and solid mechanics, structural and civil engineering, aerospace applications, electric vehicles and transportation, transmission lines and underground cables, thermal analysis, aerodynamics and fluid analysis, electrical machines, human and animal body, and more. So what are the different softwares we can use? ANSYS, GMAG, Opera, COMSOL Multiphysics, and Simulink Flux Coupling, FEMM software, and more. But we are going to focus on FEMM 4.2 now. What does FEMM stands for? Finite Element Magnetic Method, even though that one can be used for both electrostatic and electromagnetic. So FEMM 4.2 is a free open source engineering simulation software used to analyze electromagnetic and electrostatic problems using the finite element method. So it's a free download. My advice to you now, stop the video and download the software because we are going to use it from now and then. What are the key features of FEMM 4.2? Uses the finite element method, 2D planar and axisymmetric simulations, built-in Lua scripting for automation and parametric studies. Lua refers to writing program using a lightweight, high-level programming language designed to be simple, fast, and easy to embed into other softwares. Supports nonlinear magnetic materials. We can use pH curves. Visualizes magnetic flux density, field lines, and forces and torques, and runs primarily on Windows. So why FEMM 4.2? Free and lightweight, accurate for low-frequency electromagnetic problems, easier to learn compared to large commercial FEMM tools like ANSYS or COMSOL. What is the difference between planar and axisymmetrical? You mentioned that one in the previous slide. What do you mean by planar and axisymmetrical? For planar, We have the geometry is constant along the third dimension, z direction. We can build our problem in x and y direction. So we can use a certain depth. So fields do not vary along the depth, or you assume infinite depth. You are modeling a cross-section of the device. Results are given per unit depth, for example, Newton per meter, watt per meter, and accept negative axis. While axisymmetrical, the geometry is rotationally symmetric around an axis, usually the x-axis in FEMM. The model represents a revolution of a 2D profile around that axis. Fields and materials are identical at every angle. FEMM internally accounts for the 2π rotation, does not accept negative axis. For example, for the planar one, magnetic circuits and transformers, inductors with rectangular cores, bus bars, permanent magnet motors. For axisymmetrical, you can use that one for solenoids, coaxial cables, cylindrical inductors, and loudspeakers. So in conclusion, use planar when applying or analyzing a flat cross-section with no rotation, and use axisymmetrical if the geometry rotates around an axis and look the same everywhere. What will I watch in video number 3? In video number 3, we are going to start FEMM 4.2, step by step. So I presume now that you downloaded the software, we are going to use it in the next video extensively. So see you in the next video.